Jose, and thank you very much, Fernando. Welcome everybody to this webinar on flexibility. I will go through the basic behind our work, what we mean with flexibility, and the work that we did on an analysis of the flexibility needs, resources and definitions. I will present to you the categorization which we did on flexibility, and finally I will show or illustrate how these flexibility needs are diverse in a time and space dimensions, which we feel is one of the main reasons why we need different categories. So first of all, what is power system flexibility? We say that flexibility relates to the ability of the power system to manage change. But the flexibility term, as many of you are aware of, flexibility term is used in so many different types of work and projects from different communities that they are covering a large amount of different kind of aspects, which makes it really difficult to convey what we are meaning from both within the power system community but also with the outside. So this is the main background to why we started to look at this in Annex 6 of ISGAN. So this work, which I will present to you today, was made by an expert group from the Annex 6, consisting of people from Austria, Canada, France, Germany, Italy, Norway, Switzerland, and Sweden. First, we'll just show some of the background on the trends that we have in the power system. We are listing up 5 major trends which we feel are having the main impact on why we are talking about flexibility. We have the decarbonization process ongoing, which is very much influencing the power system. This is also a decentralization process where the production units are becoming more and more decentralized. We are integrating our electricity markets, increasing power transfer between markets and regions, and increasing sector coupling. We have a digitalization process which is having an extensive implementation of dependency on information and communication technologies in the system. And we have an inclusion process where we have an increasing demand of energy in the system, and this is in many different regions around the world in different from different perspectives, and increasing amount of electrification of industrial processes, for example. These trends are leading to increased volatility and uncertainty of the production and availability of electricity, and it's also leading to operation and planning of the power system closer to its limits. Flexibility as an expression has been used for over 20 years. There are a large number of definitions of flexibility. Some of them are presented here, and we have a few more in our report. This illustrates to us that it's very difficult for the power system community to agree on what we mean when we talk about flexibility. It's depending on the point of view of the one talking about flexibility, the needs which one may see, and the interest. So therefore, we propose instead to have differentiations in flexibility through categorization. We see the flexibility needs in the system considered from both the overall system perspective as well as the local perspective. These are different type of flexibility needs. We also different type of flexibility needs related to the operation of the power system and related to the planning of the power system. So we have flexibility needs ranging in time scales which are very broad. Flexibility needs and resources can be found in the whole power system. The flexibility needs are not limited to the balance of supply and demand in the power system, but can also refer to voltage, power quality, transfer capacity, and so on. And solutions to flexibility are not limited to modification in supply and demand. On the contrary, there are an unknown amount of solutions that we will see in the future. And what I want to highlight explicitly is the solutions including new rules and regulations for operation and planning. We lift up a few flexibility resources in our report, but there are a huge amount of different flexibility resources. This may come from sector coupling, for example, where we have possibilities of utilizing different time frames related to different energy carriers. Demand is a pretty straightforward flexibility resource. Energy storage is something that we are seeing an increased deployment everywhere. Conventional power plants, I mean, this is the conventional normal type of flexibility that we have or use in the power system today. But we get more and more power electronic interface power plants, which provide a different kind of flexibility resource. Different type of grid infrastructure, both relating to primary and secondary equipment, as well as the procedures as we use in operation and planning of the power system. So I will describe today the 4 different categories which we are presenting in our work. This doesn't mean that these are the only categories of flexibility that there are. One may categorize flexibility in many different ways, and we are just using these 4 categories to illustrate the value of differentiating flexibility. So we have named these categories flexibility for power, for energy, for voltage, and for transfer capacity. So I will go through each of these categories a bit and with some small examples. So with flexibility for power, we relate to the short-term equilibrium that is required between power supply and demand. This is a system-wide requirement relating to the frequency stability in an interconnected power system. The main reason why we have an increased need for flexibility for power is due to the increased amount of intermittent weather-dependent power supply. So This type of flexibility is a very short-term flexibility, and a few examples of what kind of solutions we're talking about which can support this type of flexibility is balancing provided from renewables, storage units, aggregated control of demand and supply, small units, interaction between multi-energy carrier systems, and increasing the operational limit of frequency deviations. So 2 examples of what we're talking about here. On the left side, we see a typical frequency curve after a disconnection of a large production unit. So in the cases with an increased amount of power electronic interface production in a system, we get an increased inertia of the system. This means that we are going from minimum frequency levels of one level to a decreased minimum frequency levels from the largest when we drop the largest units in the system. It's also relating to the rate of change of frequency, which is getting steeper. So these are 2 of the aspects of flexibility for power, where we need to support this kind of behavior to prevent the decreased minimum frequency level and increased rate of change of frequencies. On the right-hand side, we see another example. This curve is an old curve known as the duck curve. And why are we interested in this curve? Is the increased need in ramp speed, as we see on the right-hand side of this in the afternoon when large amount of solar power, for example, is decreased. The need to ramp up remaining units in the system is increasing. The next term or categories as we are talking about is flexibility for energy. This is a more long-term flexibility need relating to the equilibrium between energy supply and demand, but in a long-term run, relating to demand scenarios and production scenarios over time. The reason why this amount of flexibility is increasingly needed is the decreased amount of fuel storage-based energy supply in a generation mix. And what do we mean with this fuel storage-based? We mean energy supply which has built-in storage. Like, for example, we have energy fuel as oil or coal, nuclear, etc. And of course hydro, gas. And the time scales that we are talking about here is hours to years, and I have a few examples on different type of solutions that we're talking about here. Is an increased need for optimization of the value of stored energy, using pumped hydro power plants to an increased level, altering of demand behavior to follow variations in supply, and increasing interconnections between systems. A few examples on this is related to the left side. We have in the Nordic system large amount of hydro reservoirs. This has a seasonal storage fluctuations where we have for example, in the spring, minimum levels in the storages, which is something that is influencing the planning of these units. With the decreased amount of other plannable units in the system, this will be increasingly stressed. On the right-hand side, we see average generation mix in the Irish power system from April this year. Here, the Irish power system is facing a large increase in renewables and with barely any coal left. Increasing the renewables here also can be illustrated that you see that you have less and less amount of energy storage and plannable production units. The third flexibility category, as we're talking about, is for transfer capacity. This is a rather short-term aspect where you're talking about the ability to transfer power between production units and demand. Typically, we have local and regional limitations which are causing bottlenecks in the system. This results in congestion costs, but it also can result in limitations in the development of society. The reason why we're talking about this is increased utilization levels and increased both from demand side and from supply side. The time scale, as we're talking about, is minutes to hours. And then a few examples of flexibility solutions. We have, for example, already available dynamic ratings of overhead lines, which provides a flexibility on how much power can be transferred in between different regions. Topology changes is also a solution here where we are shifting power transfer between different parts of the system. Increasing nominal voltage levels is one rather straightforward way of increasing transfer capacity on existing lines. From a market perspective, we can have time variable transfer tariffs, which may influence the behavior of load and production. And we may also have a different kind of operational criteria instead of the commonly used N-1 criteria. The basics behind this need for transfer capacity flexibility relates both to the demand increase, as I mentioned, which is both related to the urbanization which is increasing in the world, and electrification, for example, of vehicles and industry. But it's also relating to the increased amount of distribution production units, where an example shown here is from Germany last summer, where we have, in areas where we have a large amount of solar production, we get a peak production from all the units in mainly the same time in a region, which is in a sense not an efficient way of utilizing the power system. The fourth one and last category, as we have lifted up here, is the flexibility voltage. This may be the most complicated part to grasp for non-power system engineers. We are relating to the ability to keep bus voltages within predefined limits, and this is a need for all in all the places around the power system. But the difficulties are mainly related to local and regional aspects. And why is this an increased flexibility need? It's because we have an increased amount of distributed generation, which leads to bidirectional flows in the distribution grid, and this leads to increased voltage deviations. This is a short-term flexibility need, so we're talking about seconds and minutes. Just a few examples on what type of solutions that can handle this flexibility need. We could have coordinated voltage control solutions, voltage support from distributed generation, storage and demand. We could have flexible AC transmission systems, so-called FACTS, voltage boosters as integrated in the distribution system, and as well as broadening the ranges which we can accept in voltage deviation. I just have one example on what this flexibility needs, how it can be illustrated with. This is a graph illustrating the power flow on through a distribution transformer during one day where we have solar production at in this on this line, and we have negative power flow, meaning that we have load in the distribution system in the nighttime and morning and evening, while during daytime we have a large amount of solar production, which makes the power flowing in a completely different direction. In this graph we also see a lot of spikes, but the main complexity that this provides to the distribution system is that we, in the end, each customer needs to have a voltage within a set range. This is for sure much easier to set when you have power flowing in one direction, because then the voltage profile will be in one direction. But when you have power flowing like this, changing from positive to minus directions, and this means that the voltage profile in this distribution system will be completely different from nighttime to daytime. And typically in this kind of system we don't have automatic control which can support the voltage for the different demand sites. There are many different kind of flexibility providers, and we have provided a few suggestions on what we need could be different providers for different kind of flexibility needs. We also like to illustrate that this kind of flexibility solutions can be implemented in a system and different levels in a system. And we are here relating to solutions for system services or control-based responses, operational procedures, and new components. A few of these examples are provided here, where we can see that in a local part of the system, we can, for example, look at solutions for demand response. In the distribution network, we can have voltage boosters supporting voltages, and different type of energy storages can be any level in the system. We can have controlled inertia response from power electronic devices, and we can have different type of control systems influencing and stabilizing the system from a system-wide perspective. Here we would also like to mention that there are many dimensions of flexibility, and we have a technical dimension where we have technical solutions that can solve anything, but we also have a commercial dimension which we need to relate to and need to develop market solutions which are supporting the different flexibility needs. And we should also realize that a resource flexibility provider may not only be providing flexibility for one type of category, but for many different kind of categories. And this can work together since there are different time domains. So these four different kind of flexibility categories we are illustrating in the space of, or in the dimensions of time and space. And the reason for this is that we need to lift up what kind of flexibility is needed where. We have flexibility for power and flexibility for energy, which is relating to the system level, but on different time scales. And we have flexibility for transfer capacity and voltage, which are more local and regional levels, and also for different time scales. Although these time scales are overlapping, and also the time scales are depending on the dynamic behavior of the power system, it illustrates that if we are just talking about flexibility in general, we may talk about completely different things. So as a summary, we state that the power system flexibility relates to the ability for the power system to manage change. And this is really a broad concept, and it is recommended to specify explicitly what you relate to when you talk about flexibility. We are proposing 4 different categories to explain this further, but we would also like to highlight that this is not the only truth that is available. You can categorize flexibility in many different ways, but if you use the flexibility term without detailed explanations and possibly categorization, it is very easy to be misunderstood. We have a report describing this in detail, which you can find on the ISGAN webpage. And so this was my final slide, and thank you very much for listening into this.